the same effect that you get with caches, with snooping on a bus, but using these point-to-point links. And we knew this was a good idea, but we recognized that there were some problems that buses have. First of all, there's this notion of intervention. Remember, when I broadcast a message on the bus, it's going to main memory, and main memory may respond if somebody else doesn't respond first. So there's these three-legged operations. How do I do this with point-to-point links? I send a bunch of messages to everybody. They arrive at different times because it's all asynchronous. Some, maybe multiple nodes discover that they have a shared copy of it. What do they do? How does memory know whether or not to respond, and so on? So there are lots of issues that we're going to have to deal with here, particularly when there's some kind of conflicts. What happens if two nodes simultaneously try to access the same cache line? Since things can get out of order, it's going to be an interesting question how you decide who got there first and how you deal with that. And finally, there's the question of ordering. When I do multiple memory operations, because I have all these links that are concurrent and are not ordered in any way, you can't even say for sure whether A occurred before B or not, because maybe they happened concurrently. And you may very well have a difficult time with this sort of thing where some events appear to occur in one order here and in a different order over there. So we recognize that those are the problems that we had to deal with before we could actually build a snooping style interconnect using point-to-point links. Snooping style protocol using point-to-point links. Okay, so just a quick slide. I expect you to go read all these papers. This is more to make the point. In 2001, this is a set of what I regarded as the current papers today, some of the best papers, and they were all looking at some notion of point-to-point links, and they were all focused on the notion that you needed to order requests. Somehow the network had to assign a global ordering so that every request entering the network was assigned at least a logical number so that you could decide in what order everything had happened. So you could serialize it even though the network was delivering messages in parallel. Well, that was 2001. In fact, in 2009, just this year, a paper appeared in HPCA back in February that still, the advance that they've made is that nodes requests still get numbered universally in the network, but they figured out how to distribute the job of assigning numbers basically by leaving gaps big enough so that you can put you can assign locally a number and only occasionally synchronize. But they're still focused on this idea that somehow you have to have this global ordering of all the requests entering the network. Well, our insight was that you don't have to do that. The network doesn't need to provide ordering. It has to inform a node when it's safe to expose the modification, which is to say, when a node wants to change something, it requests of the memory system the right to change it, which is part of the cache coherence protocol. And it may actually get the data at one point, but there may still be other copies. So there's a separate system that come along that says, okay, now all the other copies are destroyed, so you have the only copy, you can modify it and you can expose it to the rest of the world. And this is useful because computers like to speculate, and in fact, when they have a copy of the data, they proceed as if they could write, and they go ahead and modify their local copy, knowing that eventually they'll be able to expose it to the rest of the world. But they actually don't expose it to the rest of the world until they receive the second signal that says, okay, you can make it available. So we were going to take advantage of this property that modern processors have, where they regularly speculate and get ahead of what the rest of the world sees that they've done. So each processor orders its own memory operations and makes sure that if you want to achieve this sequential consistency that I talked about earlier, what you have to do is make sure that each instruction gets retired in the correct order. By retired, I mean not that you've completed the operation internally, but retirement is the point where you can make the memory changes that you have achieved with a given instruction. You make it visible to the rest of the world. So that part you have to do